everybody. For this next set of mini lectures, we're going to continue our discussion about light is a wave by talking about single slit diffraction, circular aperture diffraction. Our eyeballs are like a circular aperture, a circular opening, and also talking about thin films. Bubbles are examples of thin films. And you'll probably notice when I record at night, I get a nice reflection off my computer screen off of my glasses. Reflection fits exactly in what we're going to talk about next week. So anyway, I know that there's this reflection here that it's really hard to get rid of unless I kind of put my glasses down like this. So we'll just deal with it. In our last set of mini lectures, we talked about things that can only happen when light is a wave. And we talked about the double slit experiment. So here again, we have our double slit experiment. We've got light coming through these two slits. And then the wave fronts of light coming through those slits interact constructively to create bright points and destructively to create dark fringes, okay? If light wasn't a wave, on this screen opposite of our two slits, we would see two vertical lines of bright light, okay? But because light is a wave, because the wave is coming through these openings, the wave fronts are diffracting and then they're interfering constructively and destructively, we get this beautiful pattern of bright fringes, which we're going to play with in lab this week and next week. So you'll get to see that in person. Now, we also have a similar thing that happens when you have one slit. So let's see what happens when we have one slit instead of two slits. Now I have our experiment. Instead, I've swapped out a single slit for that double slit. My slit, the width of that slit is much larger here than the ones that I showed you previously. I've got a different color of light too. Now, on the opposite side on this screen, we're still getting light that interferes perfectly constructively and destructively whenever it passes through this slit here. It's a little bit harder to see because in the single slit experiment, our fringes are spread out farther away from the central point than they are in the double slit experiment. So here, for this blue color of light, we see a very broad central bright peak. We call this the central maximum. And then we have our first order minimum on either side. And then you can just barely tell we're starting to get a first order bright point on either side of this central maxima. Now this graph that I'm showing you here, this is the intensity of the light that is here on the screen for our interference pattern. We see that that intensity of light is certainly much stronger here for the central maximum, but then we can actually see there's a minimum destructive interference. And then we start to see a fainter, but it's there, first order bright maxima on either side of this central maxima. And actually, if I increase our graph here for the intensity, kind of blow it up, we can see we've got our bright central point here, the intensity from that bright point. We've got two minima on either side, and then we've got these little tiny, but still there, first order bright maxima on either side of the central maximum. In single slit diffraction, here we have our single slit with some width. And then we thought about that wave front, kind of that trough of the wave passing through. And each point along that wave front, we could imagine these little wavelets, these little waves that are of light that are propagating outward from that source. And then that's how you create these beautiful overlapping diffraction patterns just from one slit alone. And then the more slits you add on top of that, the more complicated your diffraction pattern can become. So we started with the double slit experiment. Now we're going to step back and look just at the diffraction pattern from a single slit experiment. Here I have set up our single slit diffraction pattern and the experiment. So this time, capital D is the width of my single slit. It's the width of the opening through which the light from my light source is coming. That light interferes constructively and destructively to create the pattern that we see on the screen, a distance x away from my slit, okay? And this pattern is different from the double slit experiment. This pattern, we have a bright central point which is broader, and then we have other bright points on either side. But this time for our single slit experiment, we are going to be focusing on the equation for destructive interference. Those are the dark spots in between the bright points. And those dark spots in between the bright points are given by this equation. It looks pretty similar to our double slit constructive interference. M lambda capital D sine theta, where this time capital D is our width of our single slit, okay? And so our central bright point is much broader, much more intense, and it is broader than our other bright points on either side. And this time we're going to pay attention to, and what's M in this equation for the single slit are the dark points, the destructive interference. So this is my M equal 1 destructive interference. That's my dark point between the bright points. And this is M equals 2, M equals 3, and so on. So actually I would call this M equals minus 1 on the other side. M equals minus 2. What we are going to do is derive an expression for the width of this central maximum. So we are going to call the width of this central maximum, we're going to call this width, I'm going to call that W. So to help us find an expression for this width W of the central bright point of our diffraction pattern here, let's again think back to our small angle approximation. So if I come over here, I've got my central line. I'm going to make a little triangle here. I've got the hypotenuse of the triangle comes up here to the dark point in between the central bright point and this first bright point on the other side, okay? And I'm going to call this distance this time y1, between the central bright point and my first dark point. I'm going to call that y1. And then I'm going to call this angle here theta 1, okay? And so then also on the other side, I can do the same thing. So I'm not drawing my triangles very well. This is also theta 1 here. So I have a triangle that has a leg of y1 and base of x. I've got my angle theta here. So tangent of theta 1 equals y1 over x. Tangent is equal to opposite over adjacent, okay? And so we remember from our small angle approximation that the sine of theta is approximately tangent of theta, and then that's equal to y1 over x. So over here in my equation for destructive interference, I can write this as m lambda equals d, and since sine theta is approximately tangent theta is equal to y1 over x, I can write this as y1 over x, okay? And I also know another piece of information, okay? y1 is this distance between the center of my bright point and the first dark spot. So that means that, where should I write that? It's important. 2y1 equals w, okay? So if w is the width of my bright spot, y1 is the distance between the center of that bright spot and the first dark point. That means 2y1. So over here on this side, this is also y1. 2y1 equals w, okay? So here where I've got y1, let's see, I can solve this equation right here for y1. y1 is equal to w over 2. So I can say that m lambda is equal to big D over X times y1 is W over 2. And now I can solve this equation for W because that's what we're trying to solve for, the width of the central bright point. I solve this equation for W. I can multiply both sides by 2x. So then I'll have m lambda times 2x equals dw. And I divide both sides by d. W is equal to m lambda 2x all over d. So what should we use for this m here? Well, remember, when we were up here, y1 was the distance between our central point and the first dark spot, okay? And so we're going to use m equal 1 here for m because we're just thinking about this central point right here, which is bounded by these first dark points, which correspond with m equal 1 in our destructive interference pattern. So this m is just 1 in this equation. So the width of my central bright point in my single slit experiment is going to equal 2 times the wavelength of my source times x divided by d. Remember, d is the width of my slit, and x is the distance between my slit and the screen where my diffraction pattern is appearing. And we're going to use this expression to help us out with some homework assignments. Also note that this equation is not on your equation sheet. If you need to find it, you have to derive it all the way back, starting with our small angle approximation and thinking about our equation for destructive interference for our single slit experiment. Let's think about our single slit experiment and all the stuff that we just derived right here. And we're going to solve a problem that's kind of similar to one of your workbook problems. Okay, so we're going to write down all the knowns as we read the problem. Our knowns, let's put them over here. Knowns. Light of wavelength 580 nanometers is incident on a single slit. So it's light's coming in through our single slit, setting up a destructive and constructive interference pattern on the other side. The observing screen is placed 2 meters from the slit, so that's x is equal to 2 meters. And the width of our central bright fringe, that's the W that we were just talking about, the width of that central bright fringe is 7.72 times 10 to the minus 3 meters. That's also 7.72 millimeters. Okay. Determine the width of the slit. So the width of the slit is capital D, question mark. To solve this problem for D, this width here, we could go to this equation. We already know W was already told us. We know the wavelength, we know x. Okay, we could solve this for D. So you could just go ahead and use that equation. Okay, so I'm going to keep on going. Let's pretend like you need to figure out what D is here, and you are working on an exam, and you only have your equation sheet, which has this equation for our destructive interference for our single slit experiment. So if we start from here, we can work down to what we can get to D, to what D should be, okay? So we're thinking about destructive interference. We know the width W here that's given to us, and we know that W is twice this y1 distance, where y1 is the distance from the center point to our first dark spot. Okay, so if we're thinking about y1, then that means that we're also thinking about m is equal to 1. So over here in my equation for our destructive interference, m is equal to 1. So I've got lambda is equal to d. I've got sine theta, but we can use our small angle approximation in geometry to switch out sine theta for y and x. So from the geometry of our system, which we just went through, we can say that tangent of this angle theta is equal to y over x. So tan theta is y over x. We also know from a small angle approximation, sine theta is approximately tangent theta, and tangent theta is equal to y1 over x. So sine theta we can replace over here with y1 over x, okay? So let's see, we can go ahead and solve this equation for d, okay? So d is equal to lambda x over y1, okay? And what did we say about y? We said that 2 times y1 gives us w, okay? So, or we could also say that y1 is equal to w over 2. So this is equal to lambda x divided by w over 2. Okay, so if you multiply by a fraction, and if you remember, if you divide by a fraction, you multiply by the reciprocal. So this is the same thing as lambda x times 2 over w. All right, so then d is equal to 2 lambda x all over w. Okay, so we're going to plug in wavelength x, w, which we've written out here for our knowns in order to get the slit width. Now, you've got to be careful because all of these need to be in the same unit. So the wavelength needs to be in units of meters. Right now it's in units of nanometers, okay? X needs to be in units of meters, and it is. W needs to be in units of meters, and it is. So 580 nanometers is the same as 580 times 10 to the minus 9 meters, because 1 nanometer is 10 to the minus 9 meters. So then this is equal to 2 times 580 times 10 to the minus 9 meters times 2 meters, and then we divide by the width of my central bright spot, which is 7.72 times 10 to the minus 3 meters. We find that the slit width in this case is 3 times 10 to the minus 4 meters, and that also equals 0.3 millimeters. Now I'm going to ask you to solve a similar problem for in your workbook. You're going to have to find the slit width d for a single slit experiment, but instead I'm only going to give you the distance between the first minima and the central maxima. So the distance between the first minima, the first arc point, and the central maxima, that's this distance y that we were talking about here in all of these problems. So we've already got some expressions here that will help you in order to work on that workbook problem.